Izuzetno zadovoljstvo kao i svaki put da dođem ponovo kući u Beograd i da vidim vas. Hvala puno što ste ovdje, hvala na pozivu. And I'll switch to English, normally because of international character of the Congress and because of our guests. And I'll be doing three presentations at this Congress. This is the first, and technical presentations will be tomorrow morning. And I'd like to give you an update on what is going on with CO2 as a refrigerant. There is something that is not that frequently being talked about, but I did talk a little bit about what is going on with this. And it fits very nicely, I think, into the motto of the conference, which is towards healthy, sustainable, and resilient buildings, settlements in cities with zero CO2 emission. I think it fits also very good in IIR stated goals that Colombo had presented this morning. I don't see her, but this is because CO2 is the only refrigerant, I would say, that is non-flammable, that is non-toxic, with zero ODP and zero GWP. So it is the only one that fits into all needs. The only problem that many people see is that it is sometimes seen as lower efficiency or higher cost of equipment, more difficult to make it, or better to say, more difficult to make it equal efficiency and equal capacity, more expensive, if you will. Regarding efficiency, I will remind you or tell to some people who don't know about that, we have done at the University of Illinois and at CTS long-term, very credible research which was funded by SAE, a Society of Automotive Engineers. It was called the CRP Cooperative Research Project, which was funded by the entire industry and really ran by industry people. And then we have been looking into various systems with the same outer size of heat exchangers, same air flow rate, and same pressure drop on the air side. Refrigerant was just free to be adjusted. Capacity was held equal to the baseline 134A system, and the only difference was coefficient of performance. It means efficiency. The project was controlled by the expert team, and that expert team had members from all most important OEMs, car manufacturers, and they had quite frankly different preferences. Some of them were against and some of them were, because it is very interesting how carbon dioxide is almost a litmus test of somebody's even positions, not only, sometimes even less rational than it should be. And then the conclusions of that project are summarized in this chart. And what this chart shows is, do you see my pointer? You do, okay, excellent. So here you have lines that are green for CO2 and lines that are red for 134A. Solid to solid, dash to dash, present efficiency, COP, as a function of ambient temperature for absolutely everything the same. Indoor temperatures are the same, flow rate, everything is the same. What can we see here is that these two systems are equal at on the road. That means speed of the engine roughly 2,000 RPM. Here was 2,000 RPM. Equality is somewhere at 35 degrees C. In the city, that equality in efficiency, same capacity, same capacity, efficiency is the same, at 25 degrees C ambient. What that means is, when you now take these results into the models of usage, that where most of the time we operate in this regime below 35 degrees C ambient over the year. Most of the energy is being used not at high ambience. That's when you need capacity, but efficiency is not so important. Then these models came to a conclusion that really less of problems with efficiency is that less energy is being used by CO2. Surprising results to many, because it is logical when people do a very simple theoretical analysis that CO2 cannot be a good refrigerant. Nevertheless, simplistic thermodynamic analysis do not take into account excellent thermophysical properties of CO2 as a refrigerant. Everything is better in thermophysical properties. With high pressure typically come relatively low reduced pressure, closeness to critical point, which increases the heat transfer. The lower compression ratio means higher efficient compressor, and so on. So now I could say that we have shown that CO2 has equal and sometimes even better performance, that it is very light and compact, and in some case equal cost. This is what many people did not believe. But we have done at CTS several conversions for Coca-Cola suppliers of their 134A bottle coolers to CO2. And we have presented, and the producers have presented also at Atmosphere America these results and statements. We have made the same cost of refrigeration equipment with the CO2, same as baseline 134A. How is that possible? Compressor is still a little bit more expensive, yet good properties in heat transfer and a little bit of good design have helped us to reduce the size and the cost of heat exchangers and offset slightly more expensive compressor still. Some of the results are indicated here in TS diagram, and with blue is 134A and with green is the CO2. For exactly the same conditions, which is here shown by these dashed lines of air, inlet and outlet from the condenser, inlet and outlet from the evaporator, and also this is here for CO2, we see that same size gas cooler or condenser brings the temperature much lower than condensation temperature in condenser. So instead of subcooling here, we were able to bring exit to the lower temperature than subcooling, and at the same time, contribution of internal heat exchanger is much more significant. Evaporation is better, heat transfer is better, suction pressures to the compressors are higher in saturation temperature, and result is a more efficient performance. What is the situation today? Wide variety of applications, real commercialization with potential to become main options in some applications, not in all. In automotive system, it is difficult to restart now after 10 years of 1234YF replacing 134A, but Daimler had announced that they are going to CO2, and I could say that currently almost 10,000 cars are commercially sold, and they are running Daimler's cars in Europe. Of course, there are some hiccups here and there, but they are going strong. Some other companies follow, some of them faster, some of them slower. Remains to be seen what will happen. But in automotive systems, we see need for CO2, where CO2 is clearly better than 134A or 1234YF, is in heat pumps. So far, heat pumps were totally neglected and not important, because whenever you have an engine with internal combustion, there is a plenty of heat. But when you have totally electric car, situation is a little bit different. I don't know whether you know, but most of current electric cars use a battery and resistive heater to heat in winter time. Can you imagine using your phone to warm you up instead of using that energy for communication? So this is a huge reduction of radius for the car. And I'm always saying that this is the first and the only so far application of heat pumps in general, where heat pump is not competing based on the cost of fuel. It is having the extension of radius as a consequence of using heat pump. That is basically the essential function of the vehicle to take you somewhere is extended sometimes 30%, depending on the car, in winter time. You 30% increase the radius of a car, electric car, if you have heat pump, and CO2 heat pump is dramatically better than 1234YF, YF, or 134A cannot even go that low. Below -5, -10 degrees C, it cannot go because it is way in the vacuum. With the changes in China, I think this will become even stronger push. You know, China was trying, and Chinese government, to help their vehicles in their automotive production, and it is going, but it is going very, very sluggishly. And they have identified that maybe the chance is to go stronger with electric cars. And with these electric cars, they have now ordered that if any company wants to get any governmental support, they have to have at least 8% of their total production by 2020, which is incredibly short, of all cars to be 8% electrically driven cars. So what that means, we will see more and more push towards heat pumps, and whether these heat pumps will be with 1234YF, just reversal of the cycle, or maybe that will be an additional push for CO2, remains to be seen. In other heat pumps, water heating, as you know, in Japan, these eco-cooled systems where they started first are going strong, increasing their number continuously, now not as fast as at the beginning, normally. In commercial, various options are implemented and expected even to increase significantly. In air conditioning, applications are going very slow, very sluggishly, actually just a few, if any. But we have done, in my labs, at the university and at CTS, experiments with CO2 and developed several systems. On the right-hand side, this is a mini split with 3 kilowatt capacity. It shows here 410A in blue and CO2 in this kind of purple. Capacity and COP at ARI conditions A, B, and C. And you see slightly more capacity with CO2 and slightly less efficiency, basically wash. But this is around here, 3.5. It becomes a little bit more difficult when you go to 6, 7 COP, as some of the best systems of today are achieving. This was the same, this was drop-in replacement. We have done extremely good systems for the Army that were with CO2, 10 tons, 35 ECU. These are air conditioners for like hospitals or sleepers or whatnot. Buses, we see long and good history, especially in Germany, in Europe, ongoing, but really not dominant at this point. Trains are getting now very, very interesting, we see very strong interest in Europe and Asia. I could tell you that we are now developing the CO2 system for the fastest train that will be seen in Asia. So I think very soon you will see some news about that. In refrigeration, in industrial, in my mind, slower than expected. I expected much faster development, but there is the largest CO2 industrial projects is now over 3 megawatts. In transportation, we see CO2 systems, carrier CO2 system on the road. Honestly, I don't know much about their commercial success, but it is going, and there are some more options for that. In commercial refrigeration, probably the steadiest, strongest inroads of a CO2 systems, rack systems, and self-contained. Normal supermarkets for rack systems distributed. Very strong show, especially in Europe. In the United States, growth is almost exponential, but the number and percentages are still relatively small. We are talking about 20–30% of a new systems are CO2. In US, much stronger in Europe. Light commercial, as I said, driven mostly by Coca-Cola, McDonald's, and others. We have demonstrated equal performance and equal cost as 134A. Now the challenge is coming really from hydrocarbons, where with the pressure to expand allowable charge, many people are changing their approach because for those people who are not familiar with CO2, it is much easier to switch to hydrocarbons because all R22 equipment is with almost no change ready to go with hydrocarbons. In my mind, this is only pushing the responsibility out of manufacturer's domain to somebody else, to governmental, because if something is acceptable, that means I am not responsible. Nevertheless, you have seen last summer these pictures. These are pictures from that high-rise building in London. Do you know what has started that fire? Not that fire had killed 76 people because of refrigerator that had started the fire. It is because of that stupid insulation that they have put outside that was supposedly fire retarding, and it turned out not to be fire retarding. But everything has started from refrigerator. That is hot point FF 175 BP. It is all identified. It is just not identified who's going to go to jail or what for that, or there will be enough settling money to arrange that. Had that been some judge to ask there, did you have any other option than hydrocarbon for your refrigerator? The answer could be yes, because we have made a refrigerator with CO2. Why didn't you use it? Because it was cheaper. Okay. That means maybe it's your turn now to pay what you have saved so far and pay consequences or pay to the victims. What is interesting to me when I look what is happening with CO2 is that application or ranges where CO2 is used is not necessarily where CO2 is good. CO2 is beating any refrigerant when you come to minus 50 degrees C, around triple point, above triple point. That's the only refrigerant that has some pressure and can be very nicely compressed above atmospheric above minus 50. And we don't see that much of application there. It is used where it is needed, not much where it is good. So maybe that will change in the future, remains to be seen. And what can we expect in the future? Significant improvements in CO2 technologies, especially improvements in the system, but more importantly, reliability and the cost. And it will be primarily in automotive, I believe because of heat pumps, in heat pump water heaters, in commercial refrigeration, and that technology, I believe, will transfer to other applications. I think we will see greater penetration of CO2 than we see now. And how will that be achieved? Using better expansion devices, mostly going into work recovery, some sort of work recovery devices, and that will be through ejectors or expanders. I happen to believe much more in ejectors than in expanders because it's simplicity, very low cost, especially compared to expanders. They look to have a very low efficiency, but when you look overall in the system performance, it is much, much better to use ejector than to use expander. And there will be more and more work in that direction. And I believe that there will be, as I said, work on simplicity and cost reduction. Whenever some technology is in its kind of infancy, everybody wants to be safe. Everybody wants to present and exercise the knowledge of new options. But these options may not be always cost effective. That's what I believe will show very soon. Scenarios, how will that happen? I think that green ecological leaning will strengthen. We will be more and more pushed by green parts of society. This is maybe, this is my kind of side comment. Every new wave of refrigerants, when you look historically, lasted shorter and shorter until we have found that there is something which is unacceptable. Maybe this will be different this time, but I'm not sure in that. Some flammability-related accidents are very likely to happen, as it did. What will be the consequences remains to be seen. And I think thanks to safety in CO2, CO2 will, in my mind, have a much greater opportunity. Today, people are talking about effect of potentially lower efficiency of CO2 on CO2 emissions in generation of primary energy. And that is always taken through LCCP, or some people use still TEWI concept, or TEWI, however you pronounce it, depends from which region you are. We see more and more stronger showing of non-CO2 generating electricity options, wind, solar, and even nuclear. In France, nuclear is dominating source of electric energy. Even in US, 1/3 are non-fossil fuel generated energy. And then this is what is going on. And there will be even stronger than today. That will dramatically affect LCCP, which has really two parts, direct and indirect effect. And the leakage is one which is related really to refrigerant itself, and energy use, that means efficiency of the system. Just as an illustration, LCCP will then look like, today it looks like this. This is LCCP, that means a life cycle carbon performance. You see here that those who value more man-made synthetic refrigerants, they say this is how it looks like. Direct effect, yes, it is significantly lower, if not zero, with CO2. And with GWP, it is certain. But efficiency and efficiency-related CO2 emissions are much lower. I would challenge this, but even if you take that into account, this is how it would look like in the case when no electric energy is being generated with CO2. And to conclude, in my mind, even stronger days for CO2 are ahead of us, and there will be great opportunities for young engineers to show who will come with more open mind, coming from the school, less kind of pushed by experience, rather by desire to show their knowledge and go more openly and freely into new technologies. And with this, I would conclude my presentation. Thank you very much.
Kao I uvek, on ima interesantno predavanje. Ja bih samo htio da napomenem da sutra u ovoj sali od 9 sati imamo nastavak normalnog kongresa, ali će profesor Hrnjak imati još 2 predavanja koja će verovatno biti interesantna kao i ovo. Hvala.
Okay, I will continue in English. If there are no any question. No?
Yes,
yes, there is question, please.
I have one question. At your university, you have been working very in the past on the ammonia refrigerant.
Yes.
Yeah.
The question is, at my university we have been working very much on ammonia, and I still work on ammonia, and we have the best and the lowest charged ammonia chiller in the world, and I have presented those at this spring. If that is a question, sorry.
Yeah, the question is the comparison between two refrigerants in the future.
Okay, we have developed at CTS the most efficient, I would say, and the lowest charge, the ammonia chiller. And we are trying to sell it and to use it. This is, for instance, numbers are like this. And I presented that in Macedonia, in Ohrid, earlier this year in whatever was May. Between 7 and 10 tons, which is 25 to 30 kilowatts, one system, has less than a pound, 420 grams of ammonia charge, 18 grams per kilowatt. This is unheard, there is nothing. Think about people that are trying to sell low charge hydrocarbons are talking about 150 grams per kilo total, which typically they use for 1 kilowatt of capacity, 150 grams. This refrigerator that was there had something like 80 grams of refrigerant in the charge. For refrigerator, which has typically less than a kilowatt, around 700–800, so this will come up to something like 150 grams per kilowatt. Ammonia is excellent fluid, the best to reduce the charge. It has 10 times almost less than that in our design. Extremely high efficient fluid, all of it. Now, the truth is in following. Ammonia is still not A1 refrigerant as CO2 is, but this is B2L. That means we don't want to use ammonia in rooms like this for air conditioning. It always has to be in indirect refrigeration with the chillers, which limits its applications to either indirectly cooled system in air conditioning or in industrial applications for that type of applications. But ammonia is far better than CO2 at higher ambient conditions, difficulty with high discharge temperatures, sometimes very high, but it is solved and solvable. So it's difficult to say. Some applications, there is no time, and I don't believe that there will be time when only one refrigerant will be chosen. There will be applications that are very good for ammonia. There are applications that are very good for CO2. And there are applications where neither ammonia nor CO2 is so good. When you look into big industrial centrifugal chillers, there are new HFOs that are non-flammable and very low GWP like 1233 ZDE, I mean, these are the fluids that are really excellent for that application, but have a niche. So there will be, I strongly believe, good applications for different refrigerants, but we are very often blindsided in our approach to what is possible and what is reasonable. I would soften these borders, give opportunity to typically not the best companies, not the strongest companies, but the second best, those who want to come to the top, will develop better systems because they have knowledge, they have commercial strength, and they will bring these systems. Sorry for talking too long.
Thank you very much.
We will talk. We can talk on the hallways. Thank you very much.
Okay, thank you very much.